Okay, so good afternoon one and all. We will start the session. So in the last sessions we have discussed about feedback configurations. Okay, so here we have voltage series feedback, voltage shunt feedback, and differential amplifiers. So we have discussed about voltage series, voltage shunt, and differential amplifiers, right? Okay, so we have derived the gain, input impedance, output impedance, and bandwidth for voltage series and voltage shunt feedback amplifiers. So today we will discuss about frequency response, frequency compensation techniques. So what are the different types of frequency compensation techniques? So this is also an important concept. So we will see what is frequency compensation. So what are the different types of frequency compensation techniques are there? Okay, see here, so in the last session, so we have discussed about voltage follower, right? So voltage follower means, so what is voltage follower? In this circuit, V0 equal to output voltage equal to input voltage. So the lowest gain that can be obtained from a non-inverting amplifier with feedback is 1. Okay, so it is a non-inverting amplifier. So in this voltage follower, the lowest gain that can be obtained from a non-inverting amplifier with feedback is 1. So when the non-inverting amplifier gives unity gain, so it is called a voltage follower, if the gain is 1, right? So here the output voltage follows the input voltage. The output voltage follows the input voltage. So V out equal to AVD, that is A equal to, we can write V1 minus V2. So here V1 equal to V in, V2 equal to V out, V2 equal to V0. So then we can write V0 equal to V in. And we have seen about AC characteristics. So in the AC characteristics, so we discussed about frequency response, right? So what is the frequency response? So here the variation in operating frequency will cause variations in gain, magnitude, and its phase angle. Okay, so all these things we have discussed in the last session. So now we will see what is frequency compensation. What is frequency compensation? So to get larger bandwidth with lower closed loop gain, frequency compensation techniques are needed. To get larger bandwidth with lower closed loop gain, frequency compensation techniques are needed, right? Frequency compensation techniques are used to get the larger bandwidth with lower closed loop gain. So there are two compensation techniques. So one is external compensation and internal compensation techniques. So in the external frequency compensation there are two methods, dominant pole and pole zero. Dominant pole and pole zero methods. Okay, first of all, what is frequency compensation? So we will see what is frequency compensation techniques. What is meant by frequency compensation? So the op-amp circuit with single break frequency is stable. If the op-amp circuit contains one break frequency, if the op-amp circuit contains one break frequency, a single break frequency, that op-amp circuit is stable, right? So if you consider the system with 3 break frequencies, this is possible due to capacitive components. So due to capacitive components, it is possible due to capacitive components, so it is possible to have the 3 break frequencies or more than 3 break frequencies, right, or 3 cutoff frequencies. So the transfer function of frequency dependent system, if 3 break frequencies, so AOL of F equal to AOL by, that is the open loop gain, by 1 plus j F by F1 to 1 plus j F by F2 into 1 plus j F by F3. If the op amp circuit contains 3 break frequencies, then the transfer function is, so AOL of F equal to AOL by square root of AOL by 1 plus j F by F1, 1 plus j F by F2, 1 plus j F by F3. Okay. Here the phase shift introduced by the system pi equal to minus tan inverse F by F1 minus tan inverse F by F2 and minus tan inverse F by F3. Okay. So with 3 break frequencies, we are getting the additional phase shift. With 3 break frequencies, we are getting the additional phase shift. So due to this, the op amp may behave oscillatory. The op amp may behave oscillatory. So then the circuit becomes unstable. So here, if you have 1 break frequency, you can say that the circuit is a stable, the system is a stable system, right? If you have 3 break frequencies, so 3 break frequencies due to the capacitive components, right? So due to the capacitive components, the break frequencies or cutoff frequencies may increase. So due to more number of break frequencies, the op amp may behave oscillatory. Okay, so it is not a stable system. With 3 break frequencies, the op amp is not a stable system. So the circuit becomes unstable with 3 break frequencies, right? The circuit is stable with 1 break frequency or cutoff frequency. The circuit is unstable with 3 break frequencies, right? So with 3 break frequencies, so we are getting the additional phase shift. So due to this additional phase shift, the op amp may behave oscillatory, right? So that's why here, what is compensation? The method of modifying loop gain frequency response of the op amp. The method of modifying loop gain frequency response of the op amp. So from 3 break frequencies to 1 break frequency. So it behaves like a single break frequency which provides sufficient positive phase margin. Okay. So frequency compensation means, so here to change the 3 break frequencies or more than 3 break frequencies to 1 single break frequency. Okay. So see the dominant pole compensation technique. So in the dominant pole compensation techniques, see this circuit here. So we have R and C components. So from this we can write, so gain equal to V0 by Vi, right? So V0 by Vi. So this we can write minus JXC, minus, see here, it is minus JXC by R minus JXC, minus JXC by R minus JXC. Okay, so that is the gain of this circuit. So A equal to minus jXc, that is the voltage. See here. So the impedance of this capacitor, so minus jXc by total impedance R minus jXc. So generally here V0 equal to minus jXc by R minus jXc into this V0 dash, right? Or here it is Vi dash. So it is A equal to this, we can write 1 by 2 pi Fc by R plus 1 by 2 pi Fc. So from this A equal to 1 by 1 plus J F by Fd, where Fd equal to 1 by 2 pi Rc. Okay, where Fd equal to 1 by 2 pi Rc. So the dominant pole means, what is the dominant pole? The dominant pole means the pole in magnitude much smaller than the existing pole, and hence the break frequency is smallest compared to existing break frequency. Okay, so the dominant pole, so it means the pole in magnitude much smaller than the existing pole. So here if three break frequencies, if you consider three break frequencies, so this we can write A dash equal to AOL by 1 plus J F by Fd into 1 plus J F by F1 into 1 plus J F by F2 into 1 plus J F by F3. Here Fd is less than, F1 is less than, F2 is less than F3, right? So see this. So open loop gain versus frequency. So it is the Fd, right? So up to this here there is no compensation. It is a no compensation. So from this break frequency the gain decreases by minus 20 decibels this per decade. So here from this point it decreases by another minus 20 decibels per decade, right? So here we get minus 40 decibels per decade. So at this break frequency again we are getting minus 20, right? So total minus 60 decibels per decade. Here the gain decreases by minus 20 decibels. So after this break point, after this cutoff frequency, so F2 again it decreases by minus 20. After F3 again it decreases by minus 20, right? So after F3 here we are getting minus 60 decibels. After F2 it decreases by minus 40. After F1 decreases by minus 20 decibels. So this portion is a, so no compensation, right? So next one is pole zero compensation technique. Pole zero compensation technique. See here using voltage divider rule. See here, this one is, this impedance is Z1, this impedance is Z2, the series combination of R2 and C2. The series combination of R2 and C2. This impedance can be considered as Z2. So here it is Z1. Okay. So using voltage divider rule, so we can write A equal to Z2 by Z1 plus Z2. So V0 by V2, right? So this point is V2, here it is V0. So V0 by V2 equal to Z2 by Z1 plus Z2. Z2 by Z1 plus Z2. Here Z2 equal to R2 minus JXC2, right? The series combination of these two components. R2 minus JXC2. So it is Z2 by Z1 plus Z2, that is equal to R2 minus JXC2 by R1 plus R3 minus JXC2. So R1 plus R2. So R1 plus R2 minus JXC2. So this we can write. So R2 plus 1 by J 2 pi of C2 by R1 plus R2 plus 1 by J 2 pi of C2. So then A becomes 1 plus j f by f1 by 1 plus j f by f2. So 1 plus j f by f1 by 1 plus j f by f2 or f0. Here you can take f2 or f0. So where f1 equal to 1 by 2 pi r2c2, 1 by 2 pi r2c2, and f0 or f2 equal to 1 by 2 pi r1 plus r2 into c2. So from this equation, so we will get f1 equal to 1 by 2 pi r2 c2 and f0 or f2 equal to 1 by 2 pi r1 plus r2 into c2, right? See here, it is a pole zero compensation curve. Okay, so if you compare these two, dominant pole and pole zero, so in pole zero compensation, the bandwidth of compensation network is greater than the bandwidth of uncompensated network. Okay, so the bandwidth of compensated network is greater than the bandwidth of uncompensated network. So the bandwidth of compensation network means, see here, so it is up to this, it is a no compensation. So the bandwidth of compensation network is greater than, okay, so it is a compensation network. The bandwidth of compensation network is greater than the bandwidth of uncompensated network. So that is about pole zero and dominant pole techniques. These are the frequency compensation techniques. Okay, so in the frequency compensation techniques, so actually the op-amp circuit with single break frequency is stable. So now consider the system with 3 break frequencies. So it is possible due to capacitive components, right? So due to capacitive components, so it is possible to have more than one break frequency. So due to this additional break frequencies, we are getting the additional phase shift. We are getting the additional phase shift, right? So due to this additional phase shift, the op-amp becomes oscillatory. So that means the system is not stable. So the circuit becomes unstable with more than one break frequency. So the method of modifying loop gain frequency response of the op-amp so that it behaves like a single break frequency which provide sufficient positive phase margin is called the frequency compensation. Clear? So what is frequency compensation? So the method of modifying loop gain frequency response of the op-amp so that it behaves like a single break frequency, not more than one break frequency. So it behaves like a single break frequency which provide sufficient positive phase margin. So it's called frequency compensation, right? So here we have dominant pole and pole zero. So see here, compare the two compensation techniques here, dominant pole and pole zero compensation techniques. So next, what is Miller compensation? So the main drawback of dominant pole compensation is the reduction in bandwidth. So the drawback of dominant pole compensation, so the bandwidth is low. Okay, so the pole zero compensation method has more bandwidth than the dominant pole. The pole zero compensation method has the more bandwidth than dominant pole compensation technique. So the main drawback of dominant pole compensation is the reduction in the bandwidth. So similarly, the value of capacitance required, here it is very large, and fabricating that large capacitance on the chip is not practicable. Okay, so the value of capacitance required here it is very large, and fabricating such large capacitance on the chip it is not practical, right? So these drawbacks are avoided by using Miller effect compensation. One is bandwidth is low, and the second one is, so the capacitance, fabricating large capacitance, large value of capacitance, so fabricating on the chip it is not practicable. So these drawbacks are avoided by using Miller effect compensation. Okay, so it is a Miller effect compensation. So the two drawbacks can be avoided with this Miller effect compensation. So in dominant pole compensation, capacitor is connected to ground from the output terminal, right? So in the dominant pole compensation, the capacitor is connected to ground from the output terminal, but in the Miller effect compensation, it is connected in the feedback path. See here, if you compare this Miller effect compensation and the dominant pole compensation, so in the dominant pole, the capacitor is connected to ground from the output terminal. See here, in the dominant pole, here the capacitor is connected, here the capacitor is connected to ground from the output terminal, right? But in Miller effect compensation, the capacitor is connected here. The capacitor is connected to so it is connected in the feedback path. It is connected in the feedback path. Okay. So with this Miller effect compensation, the two drawbacks can be avoided, right? So next we will see the parameters of op-amp. What are the parameters of op-amp? So it is input offset current. So parameters of practical op-amp. So parameters of practical op-amp. So first one is input offset current. So the input offset current IO, input offset current. So here I represents input, O represents offset. So capital I represents current, IO. So the input offset current is the difference between the currents into the inverting or non-inverting terminals of a balanced amplifier. So this we can write IIO equal to IB1 minus IB2. So input offset current is the difference between the two currents flowing into the op-amp. So IIO equal to IB1 minus IB2. So for op-amp 741, I see for op-amp 741, input offset current is 6 nanoamperes. Input offset current is 6 nanoamperes. Next is input bias current. So here the input bias current IB is the average of the currents entering into the input terminals of a balanced amplifier. The two currents, it takes the average of two currents entering into the input terminals of a balanced amplifier. That is IB equal to IB1 plus IB2 by 2. So that is the input bias current. So for 741, so IB equal to 700 nanoamperes. IB equal to 700 nanoamperes. But input offset current is 6 nanoamperes and the input bias current is 700 nanoamperes, right? Next, input resistance. So RA is the equivalent resistance that can be measured either the inverting or non-inverting input terminal with the other terminal is grounded. So input resistance is measured at either inverting or non-inverting terminal with respect to ground, right? So with the other terminal is grounded. So for the 741, the input resistance is high. So actually the ideal value is infinity, but the practical value is it is high, that is nearly it is equal to 2 mega ohms. So for some op amps it may be up to 1000 giga ohms. Okay, so in the ideal case it is infinity, that is the input resistance. Next, input capacitance. So it is the equivalent capacitance that can be measured at either the inverting or non-inverting terminal with the other terminal connected to ground. So it is also similar to input resistance. So it is measured at either inverting or non-inverting with other terminal is connected to grounded. So the typical value of input capacitance is 1.4 picofarads. 1.4 picofarads. Next one is common mode rejection ratio. So CMRR is defined as the ratio of differential voltage gain to the common mode voltage gain. So it is AD by AC. So for the 741 op amp, CMRR is 90 decibels. The higher the value of CMRR, so actually the CMRR value is high. Ideally it is infinity, right? The higher the value of CMRR, the better is the matching between two input terminals. So on the common mode voltage is low. Okay. So for the 741 op amp, CMRR is 90 decibels. So that is common mode rejection ratio. How effectively we can eliminate the noise that is decided by with the CMRR. And next, supply voltage rejection ratio. So it is the ratio of the change in the input offset voltage to the corresponding change in power supply voltage. Okay. So this can be defined as SVRR equal to supply voltage rejection ratio or PSRR. So it is delta VIOS by delta VCC or delta VEE. Delta VIOS by delta VCC or delta VEE. So for the 741 it is 150 microvolts per volts. 150 microvolts per volt. So that is about supply voltage rejection ratio. Next one is large signal voltage gain. So it is defined as output voltage to differential input voltage. So we can write A equal to V naught by Vd. So it is a high value. So large signal voltage gain. The signal here, the voltage gain is large. Okay. So ideal value is infinity. Next, output voltage swing. Output voltage swing. So here actually the output voltage changes between plus VCC and minus VCC, right? Plus VCC and minus VE. So plus VSAT to minus VSAT. Next, output resistance. So R0 is the equivalent resistance that can be measured between the output terminal with respect to ground. So here the typical value of output resistance is 75 ohms. 75 ohms, right? So supply current. So here supply current is drawn by the op amp from the supply. So for the 741 op amp, the supply current is 2.8 milliamperes. So they are the typical values. So power consumption. Power consumption is the amount of quiescent power that must be consumed by the op amp in order to operate properly, right? The amount of power consumed here it is 85 milliwatts. 85 milliwatts. Next, gain bandwidth product. The gain bandwidth product of the op amp, here it is when the open loop voltage gain is reduced to 1. The gain bandwidth product is the bandwidth of the op amp when the open loop voltage gain is reduced to 1. So next we have input offset voltage and current drift. See here what is circuit stability. Circuit stability. Okay. So a system is said to be unstable if its output increases with time instead of achieving a fixed value. Then the system is said to be unstable. Okay. So here in the unstable system, the output increases with time. The output increases with time. So instead of having a fixed value. So a circuit or a group of circuits connected together as a system is said to be stable if its output reaches a fixed value in a finite time. If the output reaches a fixed value in a finite time, then the system is said to be stable. Okay. If output increases with time, if the output increases with time instead of having a fixed value, then the system is said to be unstable. Right. So these are the parameters of the op amp. So with this I am going to stop the presentation. Thank you.